Hey AP Physics people, we're back again with another problem. This one is tabletop pulley with blocks. Another name for this device is an Atwood machine. So we have block A and block B hooked up with the pulley. And this first part, the pulley is massless. So okay, let's look at the first part of the question. All right, the first part of the question just has us really give an estimate or like just an argument on this. Um, so let's say that so we have the whole setup. Let's say that block A has a much greater mass than block B. Okay, so just gut instinct. If block A has a really big mass compared to block B, estimate the acceleration. Well, it's not going to move, like it's not going to accelerate much because block A has such a big mass. Um, so if block A is much bigger, we can say that the acceleration is close to zero. Um, and I really should have used a lowercase a here for acceleration. So, or acceleration is much less than g. G would be the, like if it was just free fall. Okay, so if you have something along that lines, then you're good. That the acceleration is going to be close to zero. All right, now down here, all right, briefly explain your reasoning. Um, this could be really straightforward and simple. It's because the mass of A is great, or it has lots of inertia. So inertia just has the tendency to resist accelerating because it has a big mass. All right, so now let's flip that and let's say that mass A is much less than B. Okay, again, let's look up here and let's just intuitively say, like, if block A had a really small mass and block B is a bigger mass, block B is just going to fall almost like it's in free fall. Well, if it's in free fall, then the acceleration is approximately g, or the acceleration is approximately 10 meters a second squared. So it's close to free fall. So it's close to free fall. And briefly explain your reasoning without driving or using equations. And you can just say that the maximum acceleration would be 10 meters a second in free fall. And so therefore acceleration would have to be somewhere close to 10 meters a second squared. Okay, now we're getting down to some harder points. Okay, so let's do the free body diagram. So a free body diagram, we have, let's do block B first. Well, block B, we have the weight of block B going down, but we also have a tension force going up. So I'm going to call that T. Okay, over here we have block A. Well, block A has the rope, so pulling, so we have a tension force here. We also have the weight of block A, and It's on a surface, so we have a normal force. Okay, let's see if I did everything. So, um, so uh, block A, on each dot, draw and label the forces, not the components. So notice that we had to label what each one of these are. If you put the force of gravity, that would be okay too. Okay, so we've drawn and labeled all the forces. So now here's where we need to do a little bit of math. So here, derive, come up with. So we need to come up with an equation for the acceleration of the blocks after they release in terms of ma and mb and physical constants as appropriate. A physical constant here, what they're getting at is g. So physical constant, like we know that that's 10 meters a second squared. Um, all right, so let's keep reading. If you need to draw anything that you've shown in part B, use the space below. Do not add anything to these figures in part B. So don't go back up and mess with these free body diagrams. We're gonna start clean here. So let's actually go to a blank page here so that we can talk about this. So this is a little bit of a harder question, but there's a trick here for Atwood machines, and I'm going to show you. Okay, so we have mass A and we have mass B. Okay, so we have these two things, and the one key concept here is that if this is a massless pulley, that these tensions are going to be the same. Like this tension going this way is going to be the same as this tension going up. So these tensions are going to be the same. All right. So here's the trick. So since these tensions are the same, I'm going to treat this as one big system here. And before we do this, I'm going to draw the other vectors here, the other free body diagram vectors. All right, so here's the forces. We have, this is the weight, so, and this is the normal force. Okay, if you look at this whole system, there's only one force here that breaks this boundary right here, and that's this force, MBG. So this is how we're going to express this. I can come over here and I can redraw this like this, MA. We got the same tension here, MB, and we have this force here. I'm going to draw this one in red now. So we have this force pulling it, MB and G, MBG. So we have this weight pulling it. Okay, so this is what I'm going to use. So I'm going to say, let's sum my forces here. It's equal to mass times acceleration. All right, so I have summing my forces and setting equal to mass times acceleration. Well, the only force I have here that's going along with the acceleration, and note that my acceleration is in this direction in the terms of my weight. So if I sum my forces here, I'm going to have only one force. I'm going to have M, B, G. And now that's equal to my mass, but this is the total mass. So my total mass, I have both of these guys. So I have MA plus MB times my acceleration. All right, so if I rearrange this for acceleration, I have acceleration is equal to mbg over ma plus mb. And there's my equation for my acceleration. All right, as a quick note here, I just want to do this really quick. What if there was friction here? Because you might get a problem where there actually is friction. And if there was friction here, you could see how that, again, breaks this system. So here, I would have something like this. If there was friction, so if there was friction, I would have this. I would have a force going this way, my frictional force, and I would have my weight here, mbg here, and remember this is a and b. So here I would have this now. So when I sum my forces, I would have mbg minus my frictional force is equal to ma. Sorry. So yeah, ma plus mb. A. Okay, let's look at this next part here. So part E. So now we're looking at, let's say that we have the scenario where it's all set up, and it says that the tension in the vertical portion of the string is T1, and we switch it. So now that there's a mass on, that the pulley actually has a mass now. So here's no mass, and now here is a mass. So we're going to say this is T1 and this is T2. Okay, so it's asking which one of these tensions is going to be more. And the correct answer is T2 is going to be greater than T1. So if you have this, if this pulley has a mass, now we're going to have a greater tension. And the reason for this is if we look at this free body diagram for mass B, if I have in this case right here, the acceleration is going to be less. So acceleration is less for this massless pulley. The acceleration is going to be less. It's not going to accelerate as fast down. You can think if this was a really, if this took a lot of energy to spin this pulley, well, the total acceleration is going to be less. Okay, so here, if we do that, then let's think about that. If I sum my forces and set it equal to mass times acceleration, well, and I look at this, I'm going to look at mass B. I'm going to have here, I'm going to have mass B, G, and here I have T. Okay, so if I look at that, like let's say that acceleration is positive, I'm going down. So let's say down is positive. If acceleration is less, if acceleration goes less, then that means that this t has to get bigger, right? So the greater that this t is, the less the acceleration is. Like think about this. If we have over here in this case, let's say that the t was really small. And I should put a g here. That if this was really small, the acceleration would be really high. But as these things get as t gets closer and closer to mbg, then we're gonna have a slower acceleration. So this case right here, so we have t2. In this scenario, t2 is greater than this t1. This tension is going to be greater than this tension because the acceleration is less. All right, so let's go through and let's look at the points here for this rubric. Okay, so points. Let's go down and check this out. So for part A, scroll down here. Part A. So again, like part A, that said that we would guess that the if mass of A, if there's a big block there, what magnitude of the acceleration will be close to 0? So this is 2 points for correct answer. So if you put that, it would be close to 0, and that's because the mass of block A is so much bigger. All right, so that's for A. And the second part, now knowing that it's going to be close to the value of 10 meters a second because A has next to no mass. Okay, part B. Okay, part B. Part B was the free body diagram. So for the free body diagram, if you had a normal force on block A, then you get a point. If you have the gravitational force on both of them, you get a point. And the tension is going up. You get a point. Okay. Part C. So part C, here was the derivation, and we ended up getting acceleration, like this is what we derived. And here's your 3 points. For using Newton's second law for each block, for combining the equations with the correct notation, so using MA and MB, knowing that the tension forces are the same in each block, and for supporting your work, so for deriving the equation. So that's 3 points. Okay, part D. Okay, part D was saying that does your equation actually back up, does it back up your justification here? So in the question it says that with this, if your mass of A is really small, what happens to your acceleration? Well, if MA goes close to 0, you would have MBG over MB. They cancel out. So acceleration would be equal to G. So in that case, like if you said for the second part that if A had really small mass, that the acceleration is going to be close to G, and then my equation backs that up. Okay, and then part E, noting that T2 is greater than T1, and coming down here and having some kind of explanation using Newton's second law. All right, so this is a tough question. Hopefully you scored some points, and let me know if you have any questions.